All right. So a few things to announce about the. I'll go through that. So what we discussed last week was, different methods for encryption, decryption. We also at the end kind of talked about other primitives, including message authentication codes and hash functions and things like that. Essentially, just to quickly go over it, we had symmetric and asymmetric encryption mechanisms. We started with symmetric. We said that basically we need a key that is distributed between two parties, the sender and receiver. Then we talked about, okay, what do we want to achieve and how should we achieve it? Long story short, we talked about stream ciphers, right? And said that basically stream cipher is this algorithm that takes a seed and expand it in a secure way. So we get a key, and then basically our key would be just basically XOR with our message, and that would be our ciphertext, right? We said that essentially in order to achieve semantic security or chosen plain text attacks, we need to use a probabilistic algorithm for doing the encryption and the decryption, because if we keep repeating the same thing at the same deterministic things, we're going to receive the same message. And the attacker may not understand what the message is, but just seeing the frequency of the message, the attacker can understand what this message potentially could be, right? So we said that essentially this key will be the results of some sort of a seed plus some nonce, right? Which this nonce is basically this random number that's been generated. And each time we want to encrypt something, we have to create a new nonce. The good thing about this nonce was it doesn't have to be secret, so you can just openly share it with the receiver. And with this, we're going to create our key, and then we're going to XOR this with our message, and we're going to get our ciphertext. So that was the story of stream ciphers. Stream ciphers are being widely used, but it's not the greatest option just because it's not the fastest option. Instead, we can do what's called a block cipher, which essentially the idea is just divide the message into multiple blocks and just permute each of these blocks into another permutation and on the same domain. So we kind of we just shift things around, but since the space for the domain for shifting these things around, permuting these things around is incredibly huge, the attacker cannot really understand what you're doing. Another thing that we do is that this permutation also has some random function to it. So basically each time we permute things, we also add some randomness to it. So we don't permute things to the same thing over and over again. Each time it will be mapped to another permutation. We talked about AES as one of the options for doing the permutation. Actually, I can take out my mask and teach today. I have the luxury of doing that. So we can have AES, which is kind of like a block cipher for doing that. And we kind of talked about blocks, like what AES is specifically. And then it has 10 rounds, it has multiple different blocks and so on. Probably some of you have spent some time and read about it. And that was the story of symmetric key encryption, right? Then we switched to asymmetric when we talked about public key and private key, right? And we essentially said that the problem with symmetric is that we need to kind of come up with an idea or some mechanism to share the key between multiple parties. Between two parties is kind of manageable. We can find ways, but let's imagine that we want to talk to 100 different people, right? So finding two keys that kind of share between 100 people is very, very difficult task. If you want to share the same key between 100 people, that would be even more difficult because now you have to think about how to keep something secret that is shared between more than 2 people, 100 people, right? So the chances that this key will be eventually released and known will be much, much more high, right? So as a result, an alternative scenario would be the public key encryption mechanism, where essentially instead of having one secret key, we have a pair of keys. We share the public key to the world. Somebody asked this on campus wire as well. So the public key is known to everybody. There's a mechanism for sharing the public key, which we didn't discuss. So generally, key management is one of the key important parts in cryptography. Usually, there is like a central server that distributes this public key to everybody. So usually, we call it certificate. For example, let's say you want to talk to Google as the website, right? How do you know that there is another website that show itself or mimic itself to be Google, right? So since the public key has to be sent from the user can, there could be somewhere in between the user and you that treat to be, pretend to be the actual user, but it's not, right? So even distributing the public key is important, and there should be some level of trust for getting that public key. And the current solution usually is that there is some central authorities that collect all these public keys. And then if you want to read the public key, you go and grab it from there instead of grabbing directly from the user. All right. So think about it as kind of like address registration. Everybody kind of registers their address into that central authority. So Google say, okay, this is my public key. Facebook says this is my public key, and so on and so forth. So for every single website, you can do the same thing, and for each entity, you can do the same thing and over, right? But generally, one thing you have to kind of pay attention is that there will be public key that will be safely shared between everybody. And once you have that, essentially for encryption, you use the public key, and for decryption, you use your private key. And that's the key difference between symmetric and asymmetric. We talked about how to create this. We talked about trapdoor functions. Specifically, we talked about RSA as one of the examples of trapdoor functions. And I think that was the story of asymmetric. Then we moved to other primitives. Say that encryption and decryption is only part of the story and part of the use case of cryptography. There's also very, very important other things that we need to do for cryptography. We need cryptography from. One key thing was message integrity, or MAX, where the idea was that when we are sending a message, we want to guarantee that this message has not been modified. The idea was we create this key tag, which essentially uses this message, use some key. So there was a message and some key. There's an algorithm, G or A, and then this creates the T or tag for us, all right? And the idea is that if only Alice and Bob has access to the key, they can be only the ones that generate and authenticate the tag. Everybody else cannot do anything. So they cannot even create a valid pair of message and tag, all right? There are security guarantees for it. There are proof for it. We didn't much discuss, but generally said that for secure MAC, we want to have be able to detect forgery attacks, and we want to also be able to detect replay attacks. These are the main two main things that we need to do. We talked about how to create MACs. PRF was one option, very simple option. And then later on, we showed that hash MAC is actually much more faster and much more popular. We also talked about should we, cascade multiple messages. So instead of creating a tag for every single message, it's better to actually kind of cascade these together and create one tag for the entire message. That would be much more faster and much more efficient. But you cannot just, just concatenate tags together, because very simply, so for example, if you have message 1, tag 1, message 2, tag 2, if you just concatenate these things and say, okay, I'm sending M1, M2, so how about I send T1, T2? The problem with this is that the attacker can take this, and then if, for example, sometime later, there is a message like this, the attacker can easily just concatenate these things together and send you a correct tag, right? So if the attacker sees M3, T3 sometime before, and now sees M1, M2 now with T1, T2, the attacker can easily just concatenate these together and send you the new tag, right? A valid tag. And if you remember, for forgery attacks, we said that the attacker should not be allowed to do this. As a result, we're kind of like adding this additional, second key to eliminate that chance. And it's guaranteed that the attacker cannot actually, using this, the attacker cannot just easily concatenate things together. All right. We also talked about hash function. Hash function, we said that it's very important thing generally, irrespective of security. There are lots of use cases for hash functions. Essentially, for secure hash function, we emphasize that secure hash function is different from hash functions. And the main thing that we want to have for your secure hash function is the collision resistance, which essentially say that it would be very, very hard for the attacker to find any two messages that has the same hash. Okay, any two messages in the entire message space, the attacker should not be able to easily find two messages that has the same hash function. And then we also talked about pre-image and second pre-image. We showed that how we can actually combine hash functions with MAC to create what's called an HMAC, which is usually what's been used regularly. So if you want to create a MAC, usually what you do is creating a hash MAC or HMAC, right? And kind of like very similar to what we showed before. This time, the only difference is that we're kind of substituting the pseudo-random function or PRF with our hash functions, right? And the reason that it's much more faster because this H function is much more faster and much more efficient than the PRF functions. And I think the last thing that we discussed was authentication encryption. So what is authentication encryption? The idea is that you want to encrypt the message, but you also want to make sure that your message has not been modified, right? Just keep in mind that symmetric or asymmetric encryption does not guarantee the integrity of your message, all right? So it just encrypts your message, and the only guarantee that it gives you is that there is no chance for the attacker to find what the message is. But an attacker can easily change your ciphertext to some other valid ciphertext, and then send that instead to the receiver, all right? So encryption itself alone does not guarantee that this attacks can be detected and can be protected. So what should we do? We should combine MAC, the integrity of the message, with the encryption, the normal encryption. And we usually call this authentication encryption. So which means that once we receive this message, it is guaranteed that this message is the original message. So that's the integrity part. And it's also guaranteed that the attacker, if he sees this encrypted message, cannot understand what the message is. So these two things together. Of course, there are two options that you can think about. First is we can take the message, we can compute the integrity tag for it. And then we have the message and the tag together, right? And then we can basically encrypt this and get C. So that's one option. The other option is that we first encrypt the message, we get C. And then we send C to our MAC function and we get C and T, right? So we basically compute the tag over the encryption rather than computing the tag over message. So we call this MAC then encrypt, MAC then encrypt. We call this one encrypt and MAC, all right? And the idea is that it can be shown that this method is not secure. There are known attacks for MAC then encrypt, which doesn't work. So what you need definitely to do is always first do the encryption and then compute the tag over the encrypted values. All right. So that's the idea of authentication encryption. There are actually, so one thing you can easily do is that, for example, send it to AES, do the encryption, and then send it to your, for example, hash MAC and get your MAC. There are methods that kind of combine these two together more efficiently. So this is what usually be used these days. We're not going to go and talk more about that in this class, but just have this idea that when we were talking about authentication and encryption, and what it is and why we need it. All right. Any questions so far? Okay. So one last thing about encryption, and before we jumping into the other topic, is digital signatures. So digital signatures is kind of like the idea of MAC. So for MAC, what we're saying is we need a key between the sender and receiver. If we have this key, then there are methods to securely compute the hash, compute the MAC, right? But what if you want to send something to 100 different users or 1,000 different users? And this is a scenario for something like a website, right? So if you want to send a message, there will be lots of users that are going to use this message, right? So that's not an scalable, solution if you want to use something like a hash MAC or PMAC or so on that use some keys. So instead, we actually use the concept called digital signature. So we basically sign this message in some way, and with the signature, we are showing that it's actually coming from us, and only us is the ones that send this. All right. And the idea is very simple to asymmetric encryption. You basically use a public and private key the same way that you use for asymmetric encryption. And this way, it's kind of like the other way around, the opposite direction of encryption. Remember, for encryption, we use public key for encryption, right? And then we use private key for decryption, right? For digital signature, we use the private key for signing, and then we use the public key for verifying. And the beauty of this is essentially, if I want to send something to the world, I use my secret key to sign it. I send it to all the users. And since all the users already know my public key, they can verify that this is actually me who's sending this message, all right? So this way it's very scalable because essentially infinite number of people can verify what I've sent. And only me will be the ones that actually sending this message because I'm the only one who has access to the secret key. Have a question?
So why do message authentication codes not work for many verifiers? Like, can't you just tag the message and publish both the message and the tag?
But in order to verify, you need a key, right? So the message authentication
Right.
is a key operation. So you need to have the secret key, same as encryption, decryption using AES. So it works for multiple people. You just need to send a key to everybody.
Wait, so how does verify with the public key work?
We're going to talk a little bit about it. So think about it as similar algorithms such as MAC. You basically the input is public key and the message, and the output is yes or no, whether this is verified or not. Kind of opposite direction of the decryption.
Okay, so that's not like leak any information about the private key.
It doesn't, yeah. So it just takes a message, public key, and just gives you the answer that whether this is coming from the user that has a secret key.
Once it's signing with private key, it's just like encrypting like a known message with a private key.
Yeah, but remember, for encryption, we're using public key. We use the public key. We didn't use the secret key, right? So for something like RSA, when you're doing the encryption, you use a public key. So for example, if I want to send a message to you, you share your public key with me. I take that public key, I take the message, I use the encryption algorithm, send you the ciphertext. And the guarantee for something like RSA and generally any public or asymmetric encryption mechanism is that you will be the only one who can decrypt this message because you're the only one who has access to the secret, right? For digital signatures, it's still the same guarantees, but the flow of information is from you to me, not me to you, because you are the one who are sending the message to the outside world, and you are the one who wants to show everybody that this message is coming from you. You want to show that this is the integrity and authenticity of this message is coming from you. So that's why you use your secret key to sign the message. So signing is different from encryption. It's different algorithm. And then send it to me. Since I have access to your public key, I can use another algorithm for verification, and then I'll verify that it's actually coming from. And the guarantee coming from this fact that only the person who has access to the secret key can successfully sign this message, right? It's kind of like similar to the notion of signature, right? So when you're seeing the signature, you're saying that, oh, I know the signature because it's coming from this person. And we're thinking about that it's difficult to forward the signature, right? So that's why it's safe to look at the signatures.
Hey, I'm just a little confused about when you said you sign it with a secret key,
Mm-hmm.
but then if you sign it with a secret key, how can the receiver use the public key to decrypt it?
It's just the way that this algorithm is designed. Similar way that the RSA algorithm is designed. Remember, we had trapdoor functions. So the trapdoor function was this function that F use the public key and the message, and we get C. And then we said that the inverse of this function, we call it I, use the secret key and the ciphertext to get the message, right? So there was this very special functions called trapdoor functions that you can compute it in one way, but inversing it without secret key is impossible, all right? So this is similar story. So we use, this time we are using I to get the M, and we are using F to get the C, basically, kind of like we are doing the opposite.
Sender then use the secret key to sign it,
Yes,
and then the receiver then use the public key
to verify.
to verify.
Yeah.
And then the attackers will have access to the public,
Attackers will have access to the public key,
but not the secret key.
not
They
the
can't sign it in the first place.
you cannot sign it, yes. Well, you can only verify, but who cares, right? So all the attackers can verify that this message is coming from me.
Okay.
And that's not an issue because you actually do want people to be able to verify. This is kind of like how it works. So you have your message. So what you do is that usually, since your message would be something very, very large, the first thing that you do is using a generic hash function to reduce it to a specific space. Remember, we said that main use case of hash function is reducing the size of a message to a smaller size. So we use a general hash function, doesn't have to be necessarily secure, and we get the smaller message or the hashed value of that message. Then what we do is that we use the inverse function. Remember, we call it I. We use a trapdoor function such as RSA, use the inverse of that using the secret key to get the signature. For verification, what we do is basically we are working in this direction. So we get the signatures as the input. So this is the input. We use the F function, the actual function, not the inverse function, but this time you're using the public key. And we get our tag, okay? So this is our tag. And what we need to do is, if you want to see whether this message has been authenticated or not, we can also always, compute the tag using the hash function that we have ourselves, compute these two tags together, and then we get the message, right? Similar story as Mac. Remember in Mac, we also, if I go back, in Mac, we also had the same story, right? Alice wants to send a message to Bob. Alice send the message. She also send the tag. Bob get the message, get the tag. She computes the tag for himself, compare the tag that he has computed versus the tag been received. And if these two matches, it means that this message has not been modified, right? Same story for digital signatures, all right? So we computed this signature, we send the signature, we get the tag. On the other hand, we compute the signatures ourselves. The tag ourselves. We compare these two, and if these two are the same, it means that the message has not been modified.
A quick question on the RSA thing. How does the receiver compute the tag on the
It doesn't, so computing the tag is just basically hashing the function of the message, basically. That's,
I'm talking about the one on the previous, like the Alice and Bob.
oh, so that's not an RSA. That's just a public secret symmetric key. So Alice has key and message. Bob has only the key. All right. So when you have a message and you have the key, the G algorithm is known, so everybody knows this. So all Bob needs to do is take G, take the message, take the key, and compute the tag. It also, Bob's another input that it gets is this tag from the actual communication. It just computes these two. If they match, means the message is not being compromised. The important thing here is that the size of the tag is much, much smaller than the size of the message. And that's why Mac does make sense. So you can have like thousands of bits and only like maybe 32 bits or something for your tag. Okay. So same story again for your digital signatures. You basically hashing the function, you compute the signature, you use the public key and F function to compute the tag. You're hashing the original message with it as well. You compare these two tags. If they ring, it means that it's coming from the actual sender, and the message has not been lost. All right. So that's the final thing about digital signatures. There are multiple ways of computing digital signatures. We made it. This one is called what's called hash-based digital signatures. All right. And again, this F function and this F inverse functions are basically a trapdoor function. It could be like ECC or elliptic curve. It could be RSA. It could be many different things. All right. Usually we use RSA for our digital signatures. Okay, so some final points. So we probably heard about the story of blockchains, right? So blockchains is actually using a bunch of these cryptography primitives, including the hash functions and digital signatures, in order to kind of give you some guarantees that things has not been modified and things are kind of like, previous things that you do is actually safe and secure and nobody can actually modify. This is actually similar to the idea of messaging integrity, right? It's probably we're going to actually have our first projects on blockchains. So we kind of like create a blockchain. Still needs to sort out the details, but most likely their first project would be creating some sort of a blockchain.
When would it be released?
Probably next week, but I'm not going to promise anything because you guys are going to get stressful. All right. So we're going to learn a little bit more about blockchains as we do the project, hopefully. There's another notion of crypto systems that is very important to know, and that's side channel attacks to the crypto systems. We're going to extensively talk about side channels, but to give you the idea, we said that, for example, AES is secure because the best thing that the attacker can do is brute forcing, right? But what we will show using side channels is that because we are doing this in hardware, doing this various things in hardware actually creates some signatures in physical boards. So for example, think about power consumption. If you're computing, values with 1 versus values with 0, the amount of power you're drawing from your circuit would be different, right? And now think about somebody who has access to measuring this power from your system. And in that case, the attacker can maybe know whether you're computing 0 or whether you're computing 1. And this could be, for example, your keys that you're doing the AES encryption, right? So the attacker basically can know exactly what your key is, or at least can know some bits of your key. And if the attacker knows that, then all these guarantees that we give you with perfect secrecy or semantic security, all of them will be gone, right? So that's the main challenge in side channels that we're going to actually talk about in this course. Another challenge with another possible attacks to crypto systems is that when you're implementing it, you're not implementing it correctly. There could be some different software bugs because at the end of the day, this is the actual software, right? So there could be bugs that you introduce in implementing it and an attacker can use it. So just, the very important rule is that you never, implement something yourself. For a crypto system, you have to follow specific guidelines and use standard methodologies. And even then, it's not guaranteed that your system will not be. So we're going to come back to this point later on in this course and talk about side channels more. Just keep in mind that the main motivation of side channels is kind of breaking these crypto systems. And we kind of talked about this before, and there was also a question on Campus Wire about quantum computing. So main things was from trapdoor, specifically for RSA trapdoor, we said that the inverse function of RSA trapdoor is very hard to compute using regular computing systems. Unfortunately, there is a known algorithm called Shor's algorithm, which shows that if you have a very sophisticated quantum computer, you can actually compute the inverse function of the trapdoor function very, very fast, within minutes. The catch is the assumption for the quantum computer is that you have a fairly complicated and advanced quantum computer, which has what we call 1,000 bits of qubits. Qubits is kind of like something similar to a transistor. So you need a computer that is very, very advanced. And currently, the technology that we have in building quantum computers is around less than 100 qubits because it's very, very difficult to combine these qubits together, mainly because of the errors that it creates. It's like 50 years before that we tried to put more transistors together and we had lots of problems. So if you go back to the history of transistors, you see that, for example, in the 50s or 40s, we managed to build one or two transistors, and it was like people won Nobel Prize for that. And now we have billions of transistors just in the pockets, right? So that's how far we have come. And now for the quantum computers, we are actually in the 50s of transistors, really. We can only put a few qubits together. And who knows, maybe 10 years, maybe less than that, maybe more than that, we will reach to the point that we can very comfortably put more than 1,000 qubits or so in our computers. And if we reach to that point, that's the end of the RSA algorithm, right? Because then you can use that quantum computer to inverse that function, and basically the entire thing about having the secret key is gone. Okay, and that's a huge problem because almost every system that we have at the enterprise level use RSA or use some public key encryption mechanisms. So we need to kind of come up with a solution for that. And the solution for that is what's called post-quantum cryptography. So this is actually a very active area of research. NIST is actually having an active call trying to standardize a new encryption algorithm that is what's called quantum resistant. There are multiple different options for it. ECC is one of them. If you heard about lattice-based computation, this is also known as a very, very interesting and very robust alternative for post-quantum crypto, because lattices cannot be inversed with quantum computers.
If like finding or which can process about 1,000 qubits on a single chip will break this RSA algorithm. Why would you ever want to? Why are people even trying to research that? Because it's gonna get rid of your you'll need to change your security protocols for almost all systems, right?
So
why is research still being done in that area?
So the research is done mostly in the post-quantum area. So finding new algorithms that are resistance against quantum attacks. So kind of getting rid of RSA and coming with a new type of encryption algorithm. That's the main research. But the research in crypto is not just about asymmetric and symmetric. There are lots of other important things that's still not solved. So things like function encryption, homomorphic encryption, multi-party computation, blockchains. These are like active areas in crypto.
Okay, now I guess my question was more like if building like that 1,000 qubit per chip computer, it's like, does it help like normal users anyway, or does it only help the hackers to break our RSA algorithm?
Oh no, so quantum computer specifically has lots of other use cases, right? So there are lots of other useful algorithms
So this is just one possible drawback.
Yeah, but it's like, why are we building atomic bombs, right? Because right, so
Sorry, I'm trying to find it online, but I can't understand any of the articles. How does Shor's algorithm scale with qubits? Because if you have like 100 qubits versus 1,000 qubits or something.
Yeah, so if you look at the RSA algorithm, the way it works is basically computing some exponents. So like you have E times, to the power of E and so on for encryption and decryption. And in order to break this, you need to kind of like try different exponents. And for a regular component, for a regular computer, computing exponents is very costly. It's very time consuming. A quantum computer can compute this exponents very, very quickly. So as quickly as just an addition. All right. So when you have multiple, and then each qubit, think about it, it's not exactly that, but technically each qubit can do one of these exponents. So if you have thousands of that, then you can test thousands of this at the same time, and then go to the next 1,000 and the next 1,000. So your search space would be very fast. So if you have 50, you can still use Shor algorithm, but it takes a very long time to actually find that. So it's similar to brute force, still maybe 50 times faster or something than regular, RSA search. But still, since that time is 100 million years or something, 50 times faster than that, it's still, 100 years or something. So it's still, with the current quantum computers, still searching is not that fast enough for it to be insecure. But if you have some numbers, sure I wasn't give you that number, then with current like 1,240 bits, for example, RSA key, you can break it within a few minutes. There's another very key things on quantum computer called entanglements, which kind of like, they're not separated from each other. They're kind of like, their states impact each other, and that's one of the key things that you can actually do the decryption very fast. Yeah, you have to learn a little bit more about quantum computers than what you will understand. But generally, the idea is that you have more workers together, and then they can like work in parallel and work in sync. And if that number is big enough, then you can very quickly. It actually grows exponentially. That's why like there's a huge difference between 50 and 1,000. So because of that exponential factor. And that's why when you reach to that number, then you can very quickly you can break ours. Okay. All right, so that's it with cryptography. Hope that, as I said, we didn't really go into the much details of the theory of it. We didn't really much go deep into some of the algorithms, like how AES is actually working or how RSA is working. But I wanted to mainly give you some overview and insights of how this works. And so later on, when we were talking about things like MAC or hash or digital signatures, they at least have some ideas with what are these things, right? But I highly encourage you to spend some time and read more about these things. Maybe these things are generally in the rest of this course. And as I said, if we actually release the projects on blockchains, we work a little bit more about these things. All right. All right, so now it's time to actually shift to another topic. Before that, so a couple of things. So I see still few people haven't done their sign-up sheets. I send an email to them. Some of them actually fill in, but I'm not sure what's going on with like 3 or 4 people who are in this class or not present in the class, and so hopefully they're safe and they're alive. But if you guys have if your Discord channel or GroupMe channel is active and everybody in there, maybe someone just send the announcement there that, if you haven't done your sign up sheet, maybe do it. So I'm not on those, so if you guys can maybe post it, maybe they're more responsive to that. Okay. Paper readings are, so you see the 3 papers that you have to read. Just a reminder that you have to pick 2 of those 3. You can pick any of those 2. Read it, use the template that I gave you in the first lecture. Write 1-page review for each one individually. Submit 2 different PDF on the locations that is on Gradescope. And by 12 o'clock today, you should be able to see the links on Gradescope. And then finally, quiz this Friday. I think it will be released at 5 or something like that. It will be 1 hour probably, or 45 minutes. Still haven't created the quiz, so I don't know exact time. I'll let you know. But it wouldn't be more than 1 hour for sure. You have a window of like 4 hours to start the quiz, but once you start it, you only have 1 hour to take it. Open book, open source, everything, just not open talking to each other, and not open, posting it on Check or somewhere else. All right. Okay, so now it's time to switch gear and talk about the new topic called malware analysis. So if you recall, before we jump into cryptography, we reach into this point that how do we trust computers, right? And the idea was that we need to start the trust from somewhere. We call that root of the trust. And then we kind of chain it or bootstrapping it all the way to the top, right? And for computers specifically, the trick is using something called Trusted Platform Modules, or TPM, which is literally a piece of hardware that we put in our systems. And we trust it because we trust the manufacturer. All right, there is a standard for TPM. Currently, we are TPM 2.0. that in order to build a TPM, here's things that you need to follow and so on and so forth. Later on in the course, we're going to say that, oh, this is not the greatest way of doing this because who knows that what happens to the TPM. And that's also a very interesting story that what happens that we don't have this, then what should we do? But it's common to understand, to accept that we can trust TPM. So once you trust the TPM, there is this well-defined, protocol or procedure called secure boot, which essentially if you remember, we do like, step by step, we read chunk of memory, we compute the hash of it, we compare it with the TPM, we go to the next step, until we basically what happens at the end was we are loading the operating system or the system software, whatever application that we want to execute at the beginning, at the initial level, and usually call that a known good state, right? So we initialize it with some state that we are completely trust, and we absolutely know that this has not been modified or this has not been compromised, all right? So that's where we were a week before cryptography. And so now the story is what happens next, right? So are we kind of like safe? Should we move on, or there are new problems? And what happens next after you load your system software or your operating system or your activity or your application is that of course you want to start executing programs, right? So the whole point of computers is a bunch of different programs that you want to run one by one or at the same time and so on and so forth. So what's the problem with executing programs? Executing programs typically involve some interaction with the outside world. This outside world could be your input and output, keyboard, monitor, printer, etc., etc. These days it's common to have some network, right? So your computer is connected to the internet. You use Wi-Fi, Bluetooth, etc., etc. And then in things like cloud or server systems, you will have other processes kind of talking to each other. You have a multi-process program that has multiple processes talk to each other, or in case of huge cloud servers, you will have multiple different applications co-locating on the same piece of hardware. Think about Microsoft Azure or AWS and Google Service Clouds and things like that, right? So servicing to many different users all at the same time, and at the end of the day, all these users will be locating on the same physical hardware, right? So this interaction in the outside world, unfortunately, is the beginning of lots of security problems, because with the outside world means that we are also communicating with a potential adversary. And the adversary can basically using this interaction, and because we are systematically weak against many different possible ways of attacking the system, the attacker can find a way to exploit the system and penetrate into the system and do what he or she wants to do. So that's kind of like where we are with dynamic security, right? So with secure boot and TPM, what we are guaranteeing is that we are kind of starting a system to some known good static point, right? But afterwards, it's kind of out of our control because we start interacting with the outside world, with the physical world, and that could create lots of problems. So we need some notion of dynamic security. So we need to kind of also be able to protect our systems when it starts executing games and when it starts to interacting with the physical world. And if you think about the dynamic world, the trick that we use with TPM and attestation doesn't work. The reason for that is the dynamic behavior of the system is not something that is known beforehand. So it's not something that you can say that, oh, I know the hash function of this, so maybe I can store this hash function into my TPM, and whenever I'm executing this program, I can compute the hash and do that. Because for example, let's say you're reading something from a sensor, and based off that sensor, you're doing something. You don't know what value from that sensor is, right? So the data that you are kind of interacting with is not something that is known beforehand. If you had known it, then there was no point of doing the sensing, right? So it's not something that you know beforehand what should be the correct value. Nobody has know this information. So any attempt of like, computing the hash and using that hash is basically meaningless because we're talking about something that is dynamically changing. All right, so we kind of needs to come up with other solutions, and that's very unfortunately, the whole bunch of cybersecurity attacks is coming from, because we're not really able to eliminate this problem. We are kind of pretty accurately able to solve the problem of static attacks using the TPM and using hash functions, but we are very, very weak against dynamics attacks, and that's the whole bunch of problems that we're facing in cybersecurity in general. All right. So yeah, so what we are seeing is that the attacker has two different options. All right. The attacker can exploit the bugs or zero-day vulnerabilities, but as we're going to talk about later, going to use some hardware characteristics of the system to attack the system. So not necessarily interacting with the system, but using this physical characteristics and this bugs in the system to attack it. So that's one way of attacking the system. The second way of attacking the system, as I said, is the interaction with the system. This interaction could be using the inputs that the attacker send, the network activity, the web activity, and so on and so forth. Right? So either through interaction or either through exploiting some bugs or some physical characteristics, the attacker can attack our system. And for the rest of this course, we're going to talk about these two possibilities and many different things that can happen in each of those.
What does zero-day vulnerabilities mean?
So zero-day vulnerability means that when we built something from the first day, from the 0 day, there was some issue with the system that we didn't know.
Is it hardware related or it can also be software?
It could be hardware or software. So when you're saying 0 days, means that by design, there was this flaw in the systems that we didn't know.
Okay, thank you.
All right. So now let's focus on this interaction part in the next few lectures, including this lecture. We're going to talk about this part. Later on, we're going to talk about how do we use some physical characteristics of some bugs in the system in order to attack. All right. So now think about this, that we want to attack a system using interaction. So think about on the adversary side, what is the goal, right? So what the attacker wants to achieve. So the attacker usually wants to achieve two things. One is stealing some information. So the attacker obviously wants to penetrate these systems to just collect some information and leave, right? So it doesn't want to do anything else with the system. The information is the one that the attacker wants. Or on the other hand, the attacker wants to do some activity. We usually call it payload. So attacker wants to actually have some impact on the system. This impact could be a digital impact, as I said before, or could be an actual physical impact to the system. So for example, the attacker wants to penetrate your system and just shut down their system, or just halt your system. The attacker wants to go and encrypt your entire memory, entire data of your system. It wants to run something that sends you lots of ads to your computer, or do something like runs your fan much more faster, or reduce the performance of your system. There are lots of different things that the attacker can do. Or when we are talking about edge cloud systems or cyber physical systems, as I started in the first lecture, this could be a physical impact. So for example, we have an autonomous car. The attacker wants to attack your system in order to stop your car, or cause your system to cause your car to cause a crash, or hit someone, or hit the wall, or so on and so forth, right? So since we are dealing with computing systems in many different scenarios, the attacker can have multiple different scenarios. But in all of those, the attacker basically wants to run some payload. And the payload is basically this piece of software at the end of the day. So the attacker wants to penetrate to your system and wants to run some software in your system. So that software can come with the attack as well. So the attacker injects this software, or the software can be just already inside your system, and the attacker just exploit this software basically. All right. So again, for example, let's say you have an autonomous car, you have a method for accelerating, you have a method for braking, right? So there are already existing software. And the attacker, all the attacker wants to do is that instead of acceleration does the brake, or instead of brake does the acceleration, right? So it doesn't really inject anything to your system. All it does is just changing the performance or changing the activities in your system. On the other hand, the attacker can inject some code with the attack to your system in order to change things and do something. So we're going to talk about these two in more details of what are these different things and why we should care. So basically, in order to do this, you need two steps, right? You need to find a way to first infiltrate the system, right? And then the second thing is creating some payload and executing that payload, right? So of course, you need to first infiltrate and then do something with it. So same as, you know, for burglary or stealing something, you have to first go into the house, then pick up the things you want and then leave, right? So the infiltration part is through the interaction with the outside world. So either the input outputs, the memory, or the networks. These are usually the three main things that the attacker can use in order to infiltrate your system. Once the attacker is in, then the question is that what the attacker can do, and that's where you want to create some payload, some software that creates some malicious activity. On this lecture, we're going to talk about this second part, that once we are in, what can we do? And usually this payload is what's called the malware. Malware is this, you know, malicious piece of software that one way or another reach into your system, and then once it's there, it starts doing something destructive. All right. So we're going to talk about this part later on. We're going to come back in the next few lectures and talk about this infiltration part. How do we actually get into that? But let's for now focus on. We found a way to infiltrate the system. Now what the attacker can do. And the reason that we want to care about this is that we want to be able to defend against this, right? So we need to first know what are the options and then finding a way to fix this issue. Any questions so far? So we are talking about malware, and malware is actually something that's very, very extensive, becoming unfortunately more and more mature these days. And essentially malware, just the definition of malware is any piece of software that created with the intent to cause some harm. All right, so that harm, as I said, could be different cases, but generally it's a piece of software that we want to run on the system in order to create something malicious, something harmful to the system. There are kind of 10 different types of malware: viruses, worms, trojans, ransomware, bots or botnets, adware, spyware, rootkits, fileless, or malvertising. In the next few slides, I'm going to quickly go over these. What are they? What are the differences, and so on. Then I'm going to talk about how do we protect our systems against this malware. All right. Let's have a quick break, and then we're going to start talking about these different malwares one more. All right. Let's continue. Okay, so let's talk about these malware types one by one. To just give you an idea, generally, as I said, all of them, the goal is to do something harmful, but that harmful thing could be a separate, different things for each of these. So, you know, the categorization is basically based on what level of harm they do, and also what how they operate. All right. So, but generally, all of them are kind of malware in general. There's a tiny difference with some of them. Some of them are very similar to each other. It's just the way that they operate is slightly different. And another thing to know is that some of these types of malwares are essentially designed to be just for spreading. So like, for example, as we talked about worms are generally not to do the harms directly, but to just spread themselves and then call in other things to do the actual harm. So it's kind of like some of them could be in different phases. So you may actually have multiple malware software together to actually create the final attacks. All right. So let's start with virus. Virus. First of all, how many of you have been like have any malicious attacks, or your system has been infected with malware with some sort? 1, 2, 3. Okay, like 30%. What type of malware was it?
I had to download this like rocket simulation software for a club.
Uh-huh.
And I got it from like some sketchy website
Uh-huh.
freshman year. And it shut down my camera
Uh-huh.
and like was controlling my computer. I think like someone was watching me through the camera.
How did you know that your system has been
Um,
compromised?
I was doing a CS project in the terminal and I realized that I couldn't access like half of my directories.
Oh,
I was
wow.
like, so
Okay.
my computer's been locked, so I had to like erase everything.
Oh, okay. So you ended up losing many things.
Yeah, but I had a lot of things in the cloud, so it wasn't that big a deal. But it was.
All right. Any other stories? Yeah, yeah. Go ahead.
I had a Bitcoin miner.
Okay.
On my computer. I found out because my computer was like weirdly slow and it would like heat up.
Uh-huh.
And I opened up the task manager.
Uh-huh.
And I think it had like a task manager detection thing. So like every time, oh, actually no. The task manager, I opened it up, and the reason I found it out was it was named like Adobe Updater or something like that. So like naturally people think it's just like Adobe Updater or something
Yeah.
like that. But it was not Adobe Updater. So
It was a miner that somebody just runs on your computer.
yeah, I guess it was like it got installed while I was installing some other program.
I see.
Probably.
So did you get a confirmation that this is indeed a miner? So did you like
No,
actually
I-
analyze the file?
No,
No,
I
okay.
just deleted it. But like
Okay.
seeing how like that it was using 100% basically was
I see.
probably something that was like.
When I was a kid, my aunt gave me a computer and we put it in the probably kitchen,
Uh-huh.
and I was looking at Age of Empire cheat codes.
Uh-huh.
So
Which one?
Age of Empires 2.
2? Okay.
The one that I was born for. So,
Okay.
yeah, I was looking at Age of Empire cheat codes, and then Age of Empires would still work and all, but whenever I was on my desktop, ads would just pop up everywhere.
Ah, okay. Good. You get malware ties. Any other?
I downloaded a version of, I think this is very bad, like in the 2000s. I downloaded Pocket Tanks.
Uh-huh.
It was like a really heavy game. I downloaded it with torrent, and this one fine day the computer just like it was so RAM intensive
Uh-huh.
somehow, even though it was a big game,
Uh-huh.
that it stopped working. The motherboard got fried.
Oh, wow. Okay. So yeah, they had to change the motherboard and everything? Wow. Okay. Well, yeah, I mean, all of us have some fire stories about this. The most common one is what's called a virus, right? So virus is kind of like inspired with the original, biological virus, which essentially is a malicious piece of code that attaches itself to another program. So for example, you said, you downloaded this piece of software that was supposed to be legitimate, for example, simulator or a game or so on and so forth. But what happened was there was this attacker that attached their code into this legitimate software. And once you download it and start executing it, the virus gets activated. So the big thing about virus is getting activated. And once it gets activated, then it starts doing the harmful things that it does. It could be increasing the temperature of systems, doing physical, impact to your system. It could be just, impacting the performance. It could be for spying, so on and so forth. There could be many different things. So generally, viruses stay dormant for most of their lifetime, and then once you actually be a victim and download the file and activate them, then that's where the virus gets activated, right? And usually viruses are designed to spread themselves as well. So usually from one computer it goes to another computer as well. So it's not just on the same computer; it tries to spread themselves as well. How many of you born after 2000? Okay. So you didn't have this. You didn't have this "I love you" email. So this "I love you" emails. You get an "I love you" email. There's this nice picture. You click on it, and then boom, you're exposed. If you're interested, I put the links for all of these different viruses and malwares. Click on it. There's a news article for it. You can read about it. But one of the very famous one was this "I love you" virus. The second type of malware is what's called worms. As I said, worms are similar to viruses, but the main goal of worms is to just spread themselves to various hosts. This is usually for example, creating a widespread attack in a company, in a government system, something like that. It's less about one specific computer. And the main thing about worms is that if you design a worm very good, I mean, the good quality worm is this worm that's it's hostless. In other words, it can work on a Windows machine, it can work on the Mac machine, it can work on an Ubuntu machine, and so on and so forth. Some of these worms are only work, for example, on specific version of the Windows or specific update of specific version of Windows. But if you have a really high quality worm, it should be able to actually spread itself to many other systems as well. Usually worms, as I said, is used to launch something else. So you want to infiltrate into one computer. The worms basically spread itself to many others. And it's then you have basically backdoor to all these different computing devices. When the time is right, then the backdoor gets activated and the original, the actual attacks happens. All right, so that's typically what the worms does. But the worm itself could actually run some payload itself. So it can, for example, depleting resources. It could modify files and things like that. If you want to know more, there's one example for the SQL data sets. It's actually like, if you use the SQL, there was this thing called SQL Slammer, which was like, creating itself into everybody who was using SQL. It was around 2003 for this one. Any questions? The third option, the third type is what's called Trojans. So Trojans, as the name suggests, looks like a benign software, very innocent looking, gets into your system and start damaging your computer. So for example, probably for your case, what you were exposed to was a Trojan. Trojans, compared to viruses, they don't usually spread themselves. It's just some piece of software that exploit your system. There is a very interesting thing called hardware Trojans, which we're gonna actually spend ample time on it. It's very important at the hardware domain. Yeah.
What's that benign?
Benign means not malicious.
Oh.
Looks not harmful. And yeah, so there are examples of Trojans as well. If you want to take a look at it, Trojans and viruses kind of like almost similar. Trojans is you can think about it more customized than viruses. It's actually the whole entire piece of software is designed to be malicious, versus the viruses can kind of like this piece of malicious code that can actually attach itself to multiple different programs, right? And then Trojans, again, is something that's, wants to go into a specific computer and infect that specific computer, rather than trying to spread itself to multiple different computers, right? Then we have ransomware, which actually these days is getting much more popular. There is lots of, actual stories about different types of ransomwares. Ransomware basically is this piece of software that once it infiltrates to your system, it will start encrypting your entire hard drive, right? So all it does is encrypting your entire hard drive. And what happens is that when you start your system, you cannot really, load your operating system. You cannot read your files and anything, because your entire hardware, your hard drive is encrypted with some unknown keys that you don't have. And since we talked about, encryption and decryption, without the key, you cannot decrypt it. So the only person that can, give you your data and your hard drive back is the attacker, unfortunately. And ransomware is basically these things that, combine these attacks with actual ransom. So literally they put a message on your system saying that if you want to, if you want your data back, give us some money or some ransom. And these days, because of Bitcoin, it's actually very easy to use ransomware. And that's why ransomware has actually become much more popular, because it's essentially a very good way of earning some money for the attackers, because they literally can get some Bitcoins and do that. There's actually last year, I think it was the entire hospital systems of Georgia, the state of Georgia, was being attacked by ransomware. And so lots of patients' data has been encrypted. And eventually the city of Atlanta in Georgia had to pay a lot of money, I think around 300,000 or something. They eventually paid to the hackers in order to get that data back. So it's pretty lucrative business these days. If you remember in the first lecture, I talked about NotPetya, right? And we said that was actually a ransomware. So this was actually another examples for that. There's another one that's very, very famous in 2017, WannaCry. Probably some of you have heard. It impacted lots of different devices. Yeah.
So is that, I mean, this is tangential, but is it illegal because ransomware comes from a different country and affects, because like my high school was a victim of ransomware, originated in China. But what's the legality of that? Can we really punish them for?
So all of them are illegal. So all of these are illegal. So it's considered burglary or thief. So it's not something that you can do or get money. That's why you ask for Bitcoin, basically. But the biggest thing is that you cannot track, right? So it's tracking the attacker, the original attacker is usually very hard. You can only track the origin of it, and usually it's somewhere that the impacted country or impacted entity cannot legally proceed against them. So for example, in the US, they cannot find people in China or other, like Russia or other countries, right? So usually the origin of the attacks usually in some other countries that's not, you cannot really, hunt them down or find them. But generally it's completely illegal, all of this. I was just joking about ransomware. So you should not use any of these malwares, actually. All right. Then the next option is what's called bots or botnets. So botnets is basically this piece of software that crawls through the internet. So it's basically like, trying to log into many different devices that it sees in their network in order to hack into them, basically gets connection from them and basically control those devices in order to get this, what's called this army of bots, this army of devices. Usually we're talking about, order of thousands or 10 of thousands of these devices together. And these 10,000s of devices are being controlled by one same server, by one same entity. And what would be the use case for that? They usually use for what's called a denial of service attacks or distributed denial of service attack, DOS or DDoS. So this DDoS attacks is basically, especially for networks is being used. The goal is you send a request to a specific server all at the same time. Think about it the same way that, back in the day when, taking courses was all open at the same time, the server goes down because like, 100, 200 people trying to, access the same server. So exactly the same thing happens, but in a malicious way. So, 10,000 devices send exactly at the same time a request to a server, and the server will be, will be halted, will be shut down just because it cannot process all these requests at the same time, or there will be a significant delay for processing all this. The very famous one is this thing called Mirai botnet. If you search for it, you will see that this is very, very, very clever attack. That what it does is attacking things like Bank of America. There's very high-profile website actually, including Facebook, that all at the same time they attack the systems and they take down those servers for a few minutes. And taking down these services for a few minutes actually huge ramifications for those entities, especially things like as big as Bank of America. If the entire website is down for a few minutes, that's a huge amount of money they lose. And the way it works is that this Mirai botnet is actually, the way it worked was scan through the networks, and they found that there are lots of routers and the smart devices like your poster or your smart lock and things like that, that their user and password is something very simple, like admin or admin nothing and things like that. And they actually tried this very simple passwords, this very known password, and surprisingly, they managed to find thousands of these devices in the internet. And they got control of all these devices, and then they managed to, synchronize them all together. And that's why, choosing the right password is very, very important. Not trying to use a password that is common, so it can be easily guessed by others.
So
Questions?
like, what was the motivation behind this Mirai attack? Like, can't imagine that the hackers benefit very much from just taking down someone else's website.
It does. Usually at the state level. So, for example, country X wants to take down servers on country Y. That's usually the main goal. And there is some usually negotiation in the back door of like, remember your servers went down, that was us kind of thing. So,
Is this also like the same stuff that's used to like mine Bitcoin?
you can run botnets to, for example, mine Bitcoin. So again, I think for your case, it was probably a botnet that's infiltrate your system to run another software. But generally, botnets is these things that you want to be synchronized all together. So the difference between botnets and regular virus is that botnets are all controlled by the same person to do something all together. And as I said, the main use case is DOS attacks, the denial of service attacks.
Would it be the same thing, for example, if like when people use bots to buy something from the internet?
That's the same notion, but let's say you really want, I think UCLA using the systems of, they assign you a time slot. But when I was an undergrad, our university was like at 8 o'clock in the morning on, for example, Saturday, the system was open. So everybody had the same, time to enter the system to take classes. And then there was this specific class that you really want to take. So you can actually write bots or to send lots of requests and increase your chances to take that class. So people actually do that. These days, if you want to like buy a PS5 or GPU, you have to run a bot to get that, right? So maybe you can create a bot to have lots of computers just keep sending requests to Sony to buy that PS5 for you. So yeah. Okay. Another group of malwares, there's adverse and malvertising. There's a slight difference between adverse and malvertising. So advert is just an actual malware that looks like an advertisement. All right, so you just download something or see something that is the malware shows as an ad, but in reality this is actually a malware. It just looks like an ad. Usually the goal of advert is doing some sort of spying on your system, on your computer, or just for annoying you so that you do something else and that actually causes another problem. So usually that's the idea of the advert. Fireball in 2017 was one of the examples. Malvertising is slightly different. So malvertising is this piece of ad that wants you to click on it. All right, so it's kind of like a clickbait. So like, oh, you won this much money, or there's this email says that, your name is on this list or so on and so forth. Or you go to this website and say, oh, you won or something like that, right? So to click on it, and then once you click on it, it usually downloads something on your computer, and that something could be a virus, could be a worm, or so on and so forth. So it's kind of like, on these quite questionable ads that you see, they typically just malvertising that they do. So there's like, a file link to it, click on it, and boom.
Just out of curiosity, so things like these show up in your spam emails all the time, right?
What's that?
Things like these show up in your spam email at times as well.
Mhm.
But the thing is, like usually the email address when the sender, it seems very legitimate. The entire interface or the way the email is written is also legitimate. But if you hover over that download or whatever button, then it actually shows you that link where it's actually going to redirect you
Yeah.
to.
Yeah.
So I was wondering, is there no way for the attacker to change that as well in order to make it absolutely legitimate?
No, you cannot. So unless you can actually find a legitimate website, but then the definition of what is a legitimate website, right? So for example, let's say if it's actually jumps into a specific website that you know before, and yes, right? But otherwise it's not. But the address of the websites are actually protected by TLS and IPsec, which are, ways of securing network.
Okay,
And that's
so-
actually backed by asymmetric encryption.
Oh, so that's why the attackers can't get.
Cannot get the public key of that
So
website
that's
to
why they can't
protect.
post their malicious software on the legitimate website.
Yeah, they
In
cannot.
order to lure you to
Yeah.
click on it.
So the whole internet is kind of like, in order to register your address, you have to go to certain protocols.
Okay. So
And that's the
it.
difference between, for example, HTTP and HTTPS and those kind of things. So yeah, I mean, we didn't talk about internet security that much.
Mhm.
But yeah, the whole bunch of these things have actually been discussed there.
Wait, so what's the difference between adware and malware? I think?
So adware is actual malware that it's on your computer, for example. So for example, remember, so if you play some games that has this like various ads in them, so some of them are actually not really an ad, they're actually a malware. They're tracking, for example, your camera, or they're tracking your GPS or something like that. So they're not really an ad. They look like an ad, but they're not. But you won't be suspicious because you think, oh, this is an ad, so I don't need to do anything. But okay, very sophisticated ad. Malvertising is something that wants you to force you to click or download or do something with it. If you do, then you download the malware, and then that's it. That's where you go from. The next option is spyware. So spyware really is not different. So all of these things that we discussed could be a spyware. The only difference is that spyware is basically, the goal of this spyware is spying. So tracking, key logging, using your webcam, etc. These are spyware. So spyware is, I mean, technically is not different type of malware in some sense. The goal, so you can have a virus that's technically a spyware because it's trying to spy on you. In spywares, one main thing is that you hear a lot is key logging. So key logging is this idea that when you're using your keyboard to type something, the keylogger can actually log this and use this. And then there are lots of, private things and confidential things that you use your keyboard from, right? So that you can see why keyloggers are actually very, very important. In my research, we actually created keylogger specifically for some computers. If you're interested, I can share my papers with you. But keylogger is actually very important security vulnerability. So spyware generally is one of those scenarios. All right. Then we have rootkits. So rootkits, as the name suggests, has two parts: the root plus the kit. So root means that the goal of the malware is getting root level access to your system. Remember, we said that we have the principle of least privilege, and we don't give access to certain, almost all the different applications in our system, unless that application really needs something, or that application has some privileges, right? So the attacker really wants to get that root level access. So what they can do is actually write a malware that achieve that root level access, right? So the kit part is basically regular malware, but the goal of the malware is to force the system to get the root level privileges. And once you have root level privileges, you can do lots of very, very dangerous things to the system. You can change, of course, the passwords and everything, so get the entire control of the system. You can do many other things with the system once you have the root level privileges. The main thing about rootkits is that rootkits is one of those mostly difficult things to detect, because usually rootkits just, since it has root level privileges, it has additional ways of hiding itself. So it can move around in your memory. It can change things that you would normally see. So for example, Chris mentioned that he used Task Manager to see whether you see that application or not. if that, malware has root level privileges, maybe it can actually hide itself from the task manager and so on. So rootkit is much more dangerous if it's actually your system is compromised with it. And if it does, it can hide itself pretty good. Okay. And finally, there is another group of malwares called fileless malware. What we have discussed so far is that at the end of the day, you have to kind of download something or run something in order for your system to be compromised. Otherwise, if you don't download anything, your system should be good, right? But the idea of fileless malware is actually figuring out ways of reusing your code or your software that already exists in your system in order to do something malicious, all right? We're going to extensively talk about fileless malware more in this course, but general idea is that you have your memory, right? And you have all your legitimate software. Then there's this buggy or malicious software that somehow get injected into your memory. Later on, we're going to talk about how to inject that part of malicious software in your system. But what happens is that you start, running programs from your legitimate part of your memory. Then you use some sort of a bug in this software to jump into this malicious part of your memory. And then once you jump to there, it's as if that you're starting executing that program. And then at that point, the adversary, the attacker takes control and then start doing an attack in your system. Of course, there are questions like how do we inject this malicious code and how do we jump from somewhere in the memory to that? These are valid questions. And when we are talking about memory safety, we're going to talk about these things.
This is basically just like a code injection attack. Right?
Yeah. All right. So that's kind of like where we are. And then the sad news is fileless attacks getting more and more common these days because it's much more easier to actually attack them. It's really hard to convince someone to download something, but it's very easy to cause someone to jump to somewhere else in the program, as we're going to discuss why. And as a result, fileless malwares these days are more popular and more effective.
I don't know if you know it, but like a few years ago, there was on WhatsApp, if you send a message like effective power, it would shut off the phone, like restart it. Is that like an example of?
It's a bug in the software, but imagine that if somebody sent you a message that caused this, then that would be an attack, right?
Yeah, it used to be like this.
Yeah, so that's a kind of a fileless attack, yes, right? Because it uses a vulnerability that exists in WhatsApp and use that to attack the system. Yeah, it's actually a very famous one. If you know the king of Saudi Arabia, Malik MBS, it was this guy who was using WhatsApp, which actually owned by Facebook, and apparently he got this questionable message from someone, and then he started the conversation and then download something, and then all of his private photos has been compromised. And then there was this article in Washington Post about this. And apparently, so there was this discussion that he came to US to do some discussion, and they actually leveraged this in order to get more leverage from him because they managed to attack using the WhatsApp and yeah.
But out of curiosity, going off this, is this the reason why WhatsApp is banned in parts of the Middle East?
I think it's only in the UAE.
It's only in the area because it's like
WhatsApp codes, not normal WhatsApp.
Yeah.
Wait, what?
Just the calls.
Yeah, the WhatsApp calls are banned.
Yeah.
Also, the messages are allowed.
Yeah. Messages.
Okay.
And there's also a whole bunch of privacy issues with WhatsApp. People say that Facebook's selling data, etc., etc. So that's also another question. But we are not saying we're not saying using or not using WhatsApp in this class. Just a disclaimer that we're not saying WhatsApp is secure or not secure. All right. And this is also an unconfirmed story, so It's not something that I'm saying is happening.
I looked it up. It looks like it was actually it's an exchange between the King of Saudi Arabia and Jeff Bezos.
Yes.
And so yeah, and then it was Jeff Bezos who got attacked.
So both Jeff Bezos. So Jeff Bezos was a separate story from the king. So apparently they kind of retaliate Jeff Bezos based on. So,
interesting.
yeah. So it's very complicated story, but read it if you're interested. So originally, I think Washington Post posted an article. They got fed up. They hacked Jeff Bezos' phone, something like that. Yeah.
Okay. Huh.
All right. Okay, so to summarize what they discussed about malware, so there are, as you see, there are various methods with various goals. Most of them are involving some sort of injection and downloading some files. So the best thing to do always is, trying to make sure that you're not downloading questionable files. But there's also another class of malwares that are fileless. And even if you don't download files, it's still your system might be exposed to this malware. Unfortunately, malware is getting more and more popular these days, just in the same trend that cybersecurity is becoming a bigger and bigger issue. All right, so one thing that you probably want to know is how to create malware. But sad news is that we're not going to discuss it in this class. If you're very interested, there are articles, there are tutorials for it. Feel free to use it. But what we are talking about is how to defend against malware. But the funniest story is that if you know how to defend, you probably know how to attack as well. So kind of similar ideas in both cases. The only thing is that usually defense, unfortunately, is much more difficult than attacks. Because as I said, when we are talking about the defense, we need to defend against all possible ways of penetrating the systems. But for the attack, we need only finding one hole and attack the system, right? So usually creating an attack, unfortunately, is usually much more easier to creating an effective defense. But of course, it's very important to understand what these attacks are to come up with defense that are actually effective. So just to answer this question and the previous question, usually there are some patterns that you can use. So you rarely see that malware is completely started from scratch. You usually take a previous malware, you change part of it, and then you create a new malware. Especially as I said, malware has two parts, right? You need a way for penetration, and you need to find a way for the payload execution. So what you can do is that, for example, usually this payload does not need to be changed. You can use the same payload over and over. If, for example, the system is patched, so no longer your penetration works, maybe you can create a new penetration methodology to attack the system. So PEDIA and not PEDIA, for example, was kind of like this idea that the penetration was slightly changed in order to attack new generation of the systems and so on. And for defenses also, we need to be aware of this and try to protect this, all right? So two things for defending against malware. One is, of course, prevention. And the second one is detection. Prevention requires various things. Mainly, we need to use best practices. That's the main reason, the main defense for defending against malware. Don't download files from the resources you don't know. Don't click on links that you don't know, so on and so forth. But things can happen always, and as a result, we need to also come up with security mechanisms inside the system so that even if the malware penetrates, they cannot do really anything. So this is more about memory protection, software protection, network protection. We don't have time to talk about this, but we will talk about this first one a little bit more in this class. But generally, prevention is not, unfortunately, is not the best solution. It's not an effective solution. And the reason for that is, the malwares can get very creative and they can attack it using different ways. As a result, we need to really find ways for detecting the system. all right, detecting the malware in the system. There are two ways of detection for malware. One is what's called a static analysis. That's how your antiviruses basically works. It scans your hard drive and looking for specific patterns, looking for specific signatures. If they see the signatures, they say, okay, this is one of the known attacks or one of the known malwares. Usually there is this huge database of different malwares, like large companies like Kaspersky or Norton or so on and so forth, Symantec. They daily, very rapid, very quickly they update their databases. And the software, basically, their antivirus software is basically what it does is just scan through your hard drive and try to see those signatures. Because at the end of the day, a malware piece of software, it has certain instructions, right? So it has a pattern. So if you're looking for those patterns, you can find it. Think about it as a large sequence of characters and then specific words within those characters. So if you can find those words, you can find those malware. All right. Questions? So that's the static part. Unfortunately, static parts can only find those signatures and also a kind of after the fact kind of thing, right? If the malware is already installed in your computer, then antivirus can find it. But malwares also, as I said, are pretty creative. So what they do is kind of like, try to change their pattern, kind of circumvent the scanning part and so on and so forth. So what you really need is being able to dynamically detect the malware. So as the malware gets activated and start doing something malicious, the ideal scenario is that your system being able to detect this, right? So that's what you usually call dynamic malware analysis, right? So how do we do anomaly detections? Anomaly detection is actually a very active area of research. And the 3 papers that you're going to read is about different types of anomaly detections, all right? So we're going to talk about, you're going to see that, different resources for doing anomaly detection, what's the different ways of the attacker can use anomaly to improve the anomaly and so on and so forth. Generally, anomaly detection has 4 main steps. The first steps is you need to extract some features from your program. Remember, the goal is that there is a program that is running in your computer and you want to say whether this is a normal program or this is an anomalous behavior. This is a potentially malicious behavior, right? So in order to make that decision, you need to extract some features from that program. All right. So what are those features? We're going to talk about it, but generally we need to extract some features. Then we need to kind of like compare these features with some known features, right? So we need to have some reference in order to compare those features with those, to say that, oh, these features are expected features, or these features are, we don't know what these features are. Then we need to kind of dynamically, monitor these features and then make a decision that, okay, at this point, we are kind of confident that these no longer agree with our reference features, all right? So we need some sort of a metric, some sort of a mechanism for detecting that, or for announcing that this is a potential anomaly. And finally, we need some sort of, a metric and a mechanism. So once we detect the malware, then what should we do, right? So these are kind of, the 4 steps of algorithm. We first extract features, then we build a reference model, then we need a mechanism for continuously checking this model, and finally we need a decision-making process of when to detect malware, and if we detect malware, what should we do next? So these are important questions, right? So what are the important features? What model to use? How to monitor dynamically? How to compare? And what should we do once we detect the anomaly? I'm going to quickly go over them in the next lecture, but you will also read a lot about this when you're reading those 3 papers. So your 3 papers is going to be actually exactly about this type of questions and answers. All right.